already in the four-term arithmetic progression, you used graphs. You reduce the problem to basically a problem about graphs, and at least for the general solution, you need to use what is everybody calls the celebrated Szemerédi regularity lemma. Can you explain the lemma?
Actually, in this RKN, there was no regularity lemma at all.
In
in RKN. There was no regularity lemma at all. There was something which was similar, much more complicated, definitely not the regularity lemma. But now people say that there are so many different regularity lemmas. Many of them are much stronger. Actually, all of them are stronger than mine. Mine was just the beginning. The real regularity lemma, and then people generalized and then simplified and so on. But definitely in the original paper, there was something where maybe you could detect the idea or notation or something, but definitely not the regularity lemma, as I maybe in 5 minutes will formulate something, but completely different.
It's completely different, but it's of the same nature, of a
similar
nature.
Yes, that actually, if you really analyze, but to almost every it's exaggeration again, to two different things actually, eventually you can come to the conclusion that they are of the same in some sense.
So maybe you describe the lemma, and then I'll ask you about the other lemma, how it
Which
compares.
I don't know because it is complicated, so that is why I don't remember this lemma. But when I heard it, then I checked it and I said, okay, it's a different thing, but still I couldn't convince anybody.
So this is your opportunity to set the record straight and say what was in which paper of yours.
Right. In this paper there was, by my opinion, but maybe this is only my opinion, no regularity lemma, something which is similar to that in some sense, but in graph theory a lot of things are similar to each. There was something similar, and then once I have the opinion, I would like to say that actually now the same story repeated itself, namely that I told the solution to my good friend András Hajnal, and after the arcade solution, and he listened. I had a note actually, so I computed everything, except I still didn't know English, and also my lectures at that time, even now, are not really something which you would give an example how to give a good lecture. So, but András is my good friend, and then also we drink a little bit while he was writing up. So the wife actually wished then the paper was a little bit shorter. So András wrote it up, and then and again I would like to thank him for his extremely great help. And then it appeared in Acta Arithmetica in 75. And then in 74, I heard a lecture given by Bolobás about the Erdős-Stone problem. And I don't want, this was actually an interesting result from the 40s. But some magnitude was not correct. And then Béla talked about this, and I wanted to improve it so that to get the exact, the sharp results. And actually for this problem was the regularity lemma done. I needed the I felt then the regularity lemma, and then suddenly it came to my mind, and this is, you can formulate a much simpler lemma than what was in the RKN, and even the proof is simpler. And then once I proved it that with and then the same story of course repeats itself. My good friend Vasek Schwatal wrote it up. And later we had a joint paper about the Erdős-Stone, the application of the regularity lemma. So that is the real story. Now people can say I am wrong, it was there, but it was not there. The regularity lemma itself appeared separately in some conference volumes, so I can prove this, that at least I didn't understand then what was in the original paper.
But you could see that the new regularity lemma could be used also in the proof for the RK.
Yes,
so
of course, it's
was
much stronger. It's stronger and stronger.
Okay, so maybe you can describe it, regularity lemma.
Well, the regularity lemma basically says that if you have a graph, let's say dense graph, so a lot of edges, then you can break the vertex set into a reasonably small number, so you can partition the vertex set into reasonably small number of classes.
Constant,
independent of n, which is extremely important. Yeah. Then if you just tell me then what precision you want, and then based on it you can determine then how many classes are in the partition. And then you can partition the vertex set so that I am not going to tell the exact result. But almost every pair of classes, if you between them you consider the edges, that is called a bipartite graph, then this is regular, which means then there is a density between these two vertex set. The density is nothing else the number of edges divided by the V1 and the size of the first set and the size of the second set.
What fraction of the total number of edges?
Yes, exactly. The fraction of, if it was a complete graph, yes, what fraction. And then if you take two, regardless how you take two reasonably big subset, epsilon percentage of the vertex set up and the vertex set down, then between them the graph still will have practically the same density.
So it is a property that a random graph would have.
Exactly. So the regularity lemma is actually kind of a philosophical statement. It's not hard to prove the regularity lemma. So it's really not such a big deal. It just says that if you have a graph that there is no total chaos, you can break it into relatively small number of classes, so that these classes and the bipartite graphs are random, and we all know we are working on this probability things, then there is nothing nicer than the random graph. The random graph has all the nice properties. So then the regularity lemma states that you can break the graph into pieces, not too many pieces, so that the resulting bipartite graphs have all the nice properties. So everything is, so that is why I call the whole graph is a chaos, because you just don't know what are the edges. But then you can break it down so with big pieces, so that there is a almost total order.
I would agree with you that it's not very difficult to prove it, but to think of it, I mean, it's actually, it's one of the most amazing things, I think, that I know in mathematics. So to think of it, it's in some sense much stronger than a Ramsey theorem. You can also interpret as that every chaos there is order, but there the order is tiny. You find a really, really tiny piece of the graph where there is fantastic order. They are all red or all blue. Here you take the graph, and essentially all of it is ordered if you work a little to organize the order. So it's just a few parts. So maybe the graph is not a random graph, or does not look like a random graph. But if you just look at 10% of the vertices here and 10% here and how they talk to each other, essentially all of these are random. I think it's sort of amazing to expect that something so strong would be true. Was very counterintuitive. So was it clear to you that it should be there, or no?
No, I don't want to claim that when I start to do something, it's clear to me. I needed.
You wanted it to be true.
I want it to be true, yes. And it happened to be true. Yes, happened to be true.